Hello and welcome to another video, this time on Stats June 2019, question 2, which is on sampling, statistical diagrams and measures under my categorization anyway. Okay, let's get started. So this question gives you a definition of an outlier, which they have to give you. They can't assume that you know what kind of definition the outlier is they're going to use, because there's lots of definitions of outliers, so they always have to give you the definition. Okay, and they say that's 1/2 interquartile ranges below Q1 or above Q3. So let's start by finding the interquartile range. So 26.6 minus 19.4, that gives us 7.2. And so if I want to work out this one or this one, what I'm going to do is 19.4 minus 1.5 times 7.2, and that gives me a value of, let me just quickly check on my calculator, 8.6, or 26.6 plus 1.5 times 7.2, and that gives you a value of 37.4. So at that point we can see this one and this one are outliers, so we need to represent it as an outlier by using a little star. Try and be more precise than me. Then the next one is going to be the lower quartile, so sorry, not the lower quartile but the minimum value. Whoa, that was a bit wonky. And on the other end, we don't have any outliers, and so we're going to go up to 32.5, and that's that one done. Yeah, and that's the box plot completed. Okay, here's a scary bit. Using your knowledge of the large data set, suggest from which month the two outliers are likely to have come. Well, they're cold, yeah, and we're in Beijing, and all of the data set only goes from May to October. So all you've got to do is say, well, October's the coldest month, so October. Now, I've had a sneaky look at the mark scheme, and I'm amazed that they don't accept May either. Basically, they assume that everybody knows that May is warmer than October, and it's like, is it? Really? That was the only answer they'd accept. But yeah, there we go. So October, as it's the coldest month. So we needed to know about the large data set there. We really did. Okay, next we've got the summary statistics, and they asked us to show that the standard deviation is this. Well, if you look carefully in the formula book, this weird SXX notation, they actually give you the formula for the standard deviation, and it's dead easy. You just have to go, okay, square root of 4952.906, divide it by 184, and that gives you 5.188, which is 5.19 degrees Celsius. Hopefully that's nice and easy. This is the formula we normally use, but this is the alternative formula, and that's because SXX is basically sigma x squared minus, and let me just write this down over here, sum of x squared over n. That's what that equals, and when you actually do SXX divided by n, you actually end up with sum of x squared over n, and divide this term by n, and you suddenly have the mean squared. Yeah, that's what, that's essentially why it works like that. But yeah, I wouldn't worry about it too much, just use the formula. Okay, part D. Now, sneaky normal distribution in the middle of the question. How sneaky? Because, and that doesn't bother me because we've recently done the normal distribution, we've done exactly this. We're essentially looking for values on our normal distribution so that we find the top 10% and the bottom 90%. So we want this to be 0.1, let's call this B. This is 22.6 because it's the mean. Let's call this A, and that's going to be 0.1 as well. We're trying to find the value which gives us the bottom 10% and the top 10%. And you do that using inverse normal. So we're trying to find the probability that T is less than or equal to A, and we want that to equal 0.1. Yeah, you can now do this on your calculator completely using just the inverse normal distribution. And so I'm going to do it on my calculator, and I think you get 15.95. Let's have a little look. Yep, 15.95. We're going to do the same thing with this end. Now you might write that down first, but you might prefer then to swing that around to make that 0.9, just because calculate an inverse normal only works with less than or equal to, and so you need to bear that in mind. And so that comes to, I'll just quickly work it again, I think it's 27 point something, inverse normal, okay, 0.9, 5.19 and 26.6. Let me just check I've typed that in correctly. Oh, I've typed in as 26.6, not 22.6. You know, it's like so easy to miskey something, isn't it? And that comes to 29.25. And so the 10th to 90th interpercentile range is just a subtraction of these two. Okay, cool, done. Okay, last bit, more large data set misery, I'm afraid. Now, I've actually taken a screenshot of the large data set. We're dealing with Beijing, yeah? And Beijing and all of the other international ones, that's Jacksonville and Perth, they don't have much data, yeah? Haven't got all the columns that the English ones have. So we can only use these columns, yeah? Now the most obvious one, which isn't appropriate for a normal distribution, is obviously the last one, the daily mean wind speed Beaufort conversion, because the data is not quantitative. So daily mean wind speed Beaufort, as this data is qualitative, not quantitative, or just not quantitative. And so obviously you can't do any kind of normal distribution stuff on data which isn't quantitative. You can do it actually on discrete data. You just approximate it to using continuity corrections. Yeah. So we do, think about when we approximate the binomial with the normal. It's possible to approximate discrete distributions using continuous distributions. And so you can't just say, oh, some of this data is discrete. But what you can say, look at the rainfall column. 0, 0, 0, 0, 0, 0, 0, 20, 0, 6, 0, 0, 0, 0, 0. Does that look like a normal distribution to you? No, it really doesn't. So another obvious one would be rainfall. Rainfall, since the data is heavily skewed to 0. Yeah, data which is heavily skewed is data which is bunched up like that, or it can be the other way around, negatively skewed like that, or something like that. That just doesn't look like the symmetric skew that we're used to on a normal distribution where everything's bunched up round the middle. Yeah, and it's a shame they don't teach skew properly anymore. Like it's sort of like missed off the syllabus accidentally. That's what it strikes me. But those are the two categories I would go for as not being suitable for modelling by a normal distribution. This one I've just said because the data is not quantitative. This one, since the data is heavily skewed, so I'll give them my reasons. Okay, yeah, I hope that makes sense. Keep up the hard work and well done. Bye bye.